All right, so 11.1 is uncertainties and errors in measurements and the results. So we're talking about uncertainty values and significant figures. There are two types of errors. There's random errors or uncertainties, which is an equal probability of reading something too high or too low from one measurement to the next. Examples of things that can give random errors would be changes in the surroundings. So if the temperature of the lab dramatically changes from one trial to another, or air current in the classroom could cause those changes. Systematic error is when the measurements are different by the same amount. And the most common systematic error is when you don't read the meniscus from the bottom of the curve. So you're constantly looking down to it or you're constantly looking up. You're not eye level with that meniscus. Some other things could be overshooting the titration. So when you're adding your base to your acid, for example, you're always going past the end point. If your indicator doesn't match what it should match, so the indicator is changing colors before or after the equivalence point, or if you lose heat to the surroundings. So if you are looking at the amount of heat given off, like when we were burning the Cheetos, and you don't contain all of that heat's lost to the surroundings. Now it could be that the heat's being absorbed by the stir that you have in the beaker, or the thermometer itself, or the wire gauze that the beaker is sitting on. So it doesn't necessarily mean it's lost to the air. Precision and accuracy. Precision is how close those measurements are to each other. Accuracy is how close it is to the true value. So if you're doing your IA and you're looking at or you're calculating heat enthalpies, you could do a percent error and see how close your values are to what it actually should be. Significant figures, everything that you know for certain plus 1. So for example, on our first ruler here, we can only estimate the first digit, the tens place probably. So we could say that this is roughly 20 centimeters. That's as much as we can. This is our estimated digit. In the second ruler, we can estimate the ones place because we know for certain the tens. So we could say that this is maybe 22 centimeters. And then down here in our final ruler, it goes to the tenths place, to the ones place, so we can estimate the tenths place, one past what we know for certain. So we know 20 for certain, and then 1, 2, we know 2 for certain, and then we're going to estimate that tenths place. When you report measurements, you should always have the measurement, the uncertainty, and the unit. So make sure in your IAs you include all three of those things. The uncertainty is plus or minus 5 for the smallest magnitude. If you are reading it from a ruler, it's plus or minus 1 if it's given off of a digital device. If you're doing a database IA, then you're going to want to use that plus or minus 1, the smallest magnitude, if your database does not give you uncertainty values. The uncertainty should also only contain one significant figure, although percent uncertainties, sometimes you'll see those listed with more than one. If you're trying to find the average of values, you would average them like normal, add up all of, for example, the velocity here, you can add all up these and then divide by 6. That gives you your measurement. To find the uncertainty, you do the maximum value minus the minimum value divided by 2. So you would take the largest value, which is 0.37, and then you would subtract the smallest value, which looks to be 0.28, and then divide by 2, and that's going to be your uncertainty. So if we look at our example here, we're doing an average for concentration. So here's our units of concentration and then our 3 measurements. So to find the measurement or the answer, quote unquote answer, we would take our 3 values and add them together. and divide by 3 since we're given 3 values. So it would be 0.0983 moles per decimeters cubed. To find the uncertainty, we would take the maximum value, so the largest value that we have, minus the smallest value. Whoops, sorry, that should be 49945. And then divide it by 2. And so we get an uncertainty of 0.00525. Since uncertainty can only have one significant figure, we would say that it's going to be plus or minus 0.005, which means we can't go past that third decimal place in our measurement. So 1, 2, 3. So we can't go past the 8 in our measurement because of our uncertainty. So it would be 0.098 plus or minus 0.005, and then we would want our units moles per decimeters cubed. Percent or fractional uncertainty. This is used when you are multiplying and dividing. Typically, we don't use it any other time. To find the percent uncertainty, you take the uncertainty, which is 0.1 in this problem, and then you divide it by the measurement, 25.4, and that gives us, multiply it by 100, and that would give you a percent of 0.4. The fractional part of that, you would just ignore the times 100, and so for the fractional, it would be 0.004. For multiple readings, again, when you're adding and subtracting, you're going to add your uncertainty values. When you're multiplying or dividing, you add the percent uncertainty. So that's why you need to know how to find the percent. So for example, here we have a burette. It has a given uncertainty of 0.02. So sometimes the glassware has that on it itself, usually up at the top or wherever they put the manufacturer's name. So we're going to subtract the final minus initial. So the volume that was actually added from this burette would be 26.31. And then for the uncertainty, you add your uncertainty values together. So 0.02 plus 0.02 gives us 0.04. So we would record that value added, or the volume of the liquid added, as 26.31 plus or minus 0.04 centimeters cubed. So when you're working on your IAs, make sure that when you're taking the average of values or you're taking subtracting the volumes, that you're including that uncertainty correctly.